Hi everyone. Welcome back to Dave's Math Channel. I'm your host David Tear, and this is my continuing feature on the Math Lovers book. I'm starting a new chapter today. I'm starting chapter 3, which is on real numbers, and I'm going to start with section 3.1, which is how to convert fractions to decimals. So anyway, let's begin. Chapter 2 was about natural numbers or counting numbers, as they used to be called. Now I'm going to talk about real numbers, so not just fractions, but also irrational numbers. Those comprise what are called real numbers, which are pretty much all the numbers that most kids learn in school. You know, maybe if you go into a STEM field, you'll learn about complex numbers at some point, but I am going to talk about complex numbers in chapter 4, so that'll be kind of fun because that's something that most people don't learn. But it is part of my Math Lovers book series, so just a little heads up on that. But section 3.1, the first section I'm doing on real numbers, I'm going to talk about how to I'm going to talk about fractions and decimals. And there's two parts to this section. I'm going to talk about how to convert a fraction, an arbitrary fraction or an arbitrary rational number, if you like, into a decimal. You guys probably learned how to do this when you were in grade school. Maybe forgot. I don't know. When you're learning long division, I'm sure you guys all learned this at some point. Doesn't seem to be something people like particularly, and maybe you learned it when you had to learn it, and maybe you forgot how to do it since then. And people do seem to be forgetting how to do basic arithmetic these days, maybe due to the prevalence of calculators and computers and the fact that people don't have to do arithmetic the way they used to. But I think there's more involved than just that. I think also our educational system's going to hell. But I don't want to get into that. Anyway, I am going to talk about how to convert from fractions to decimals. So let's begin with that. I'm going to go over 3 examples here. So in the first example, suppose we want to calculate the decimal representation of 7 over 25. The fraction 7/25, if you like. And a fraction is really just a division. So when you see a fraction like 7 over 25, it really means you're just dividing the number 7 by 25. And you might remember when you were learning long division that when you're doing, when you're dividing a number by another number, the thing that's called the divisor goes on the outside. In this case, that's 25. That's just a denominator. And the thing that you're dividing into is called the dividend. That goes on the inside of this kind of funny upside down L shaped symbol. So that's how you set it up. And then the first step here is you want to find the largest multiple of 25 that's less than 70. I mean, we would start with 7, but since 7 is already smaller than 25, we know that the number before the decimal place in this quotient has to be 0. Because whenever you're doing a fraction that's less than 1, the decimal always starts with 0, as it does in this case. So then you just kind of shift things. So now you should be thinking about, how many multiples of 25 go into 70. So if you like, we're kind of multiplying the um, the divisor by zero point 0.1. We've just shifted everything one space to the right. So we know that 2 times 25 is 50, and 3 times 25 is 75, and 75 is too big. So 50 is the largest multiple of 25 that is less than or equal to 70. So that means that the next number in the decimal expansion is a 2. The next digit's a 2, which goes just to the right of the decimal place. The next step is we do a subtraction, and we're subtracting 5 from 7, if you like 5.0 from 7.0. I prefer not to think about where the decimal place is. I just find it easier to think about the multiples of 25 and keep shifting things as we go. So anyway, we wrote it 2. That was our next digit in the decimal expansion, but we're not done because we have a non-zero difference. Our difference now is 2, but now we have to multiply that by 10. So we really have 2.00. If you ignore the decimal place, that's just 200. And 200 divided by 25 is 8. You can check that yourself. So that means that the next number in the decimal expansion is an 8. And then since that was exact, we subtract 200 and we're left with 0. So this is an exact decimal expansion. This is what's called a terminating decimal. And I might as well tell you guys, every rational number, either its decimal expansion either repeats or it terminates. Most of them repeat, but some of them terminate. And it turns out the ones that terminate are the ones in which all the prime divisors of the quotient or the denominator, if you like, are powers of either 2 or 5. If there's no other prime divisors than 2 or 5, then the decimal will always terminate. And since 25 is just 5 squared, this is a case in point. The decimal expansion of 7 over 25 terminates, as we've seen. But this is kind of a rarity. Most of them don't terminate. I think the next two examples I'm going to give are ones that repeat, and those are more the norm. So anyway, example 2, how about computing the decimal expansion of 1 over 13, 1/13, if you like. And we set it up the same way. We do the same thing we were doing before. We're dividing 1 by 13, which means we put 13 on the outside, 1 on the inside. But now we're going to get 2 zeros when we start this one because 1 is less than 13. That means that we can't subtract anything. So we write a 0 to the left of the decimal place. But then we have to write another 0 because 10 is still less than 13. Even when we add another 0, we're still less than the quotient. So we keep going, right? 0.0. And now we bring down another 0. Now we have 100. And the smallest multiple of 13 that's less than 100 is 91. That's 7 times 13. That means that the third number we write on top is a 7. So far we have 0.07, or if you like 007 for James Bond. Kind of reminded the scene in Goldfinger where he stops the atomic bomb when there's exactly 7 seconds left, and then the timer reads 007, which I thought was kind of amusing. I don't know why I just thought of that. But anyway, so we have 007, but then we have when we do the subtraction, we're left with 9. We bring down another 0. Now we look for the biggest multiple of 13 that's less than 90. That happens to be 78. So we bring a 6 up. Now we have a 6 next to 7. So far we have 0.076. We keep going. When we subtract 78 from 90, we get 12. We bring down another 0. So now the smallest multiple of 13 that's less than 120 is 117. Which is 9 times 13, so we bring a 9 upstairs. And when we subtract 117 from 120, we're left with 3. And we bring down another 0 again. So now we look for the smallest multiple of 13 that's less than 30, and that's 26. So since that's 13 times 2, we write a 2 upstairs. And then we subtract 26 from 30, that gives us 4, and we bring another 0, that gives us 40. And this time we can subtract 39, which is 3 times 13. So when we subtract 39 from 40, we're left with just 1. But notice we started with 1. So now we're left with something that looks exactly like what we started with. And that means that our decimal is going to start repeating from this point on. So we're going to end up doing exactly the same thing we already did, which means the next digit in the decimal expansion is going to be a 0 again. And then everything is going to happen just like it did before. We're going to have another 7, another 6, another 9, so on. So what we do, the way we show that this decimal repeats is we put a line above the digits that repeat. And those are 0.76923. So our result is 0.076923 repeating. And the way we indicate that those digits are repeated is we put a line above those 6 digits. This is a decimal with a period of 6. So pretty large period. Anyway, that's what we get when you compute the decimal expansion of 1/13. One more example. This one's a lot easier. But this kind of shows you a third thing that can happen. It doesn't have to start repeating right away, as this example shows. Suppose we're computing the decimal expansion of 8/15, 8 over 15. So like before, we put the 15 on the outside, the 8 on the inside. And since 8 is less than 15, we have a 0 to the left of the decimal point. But now we add another 0 to the right. Now we're subtracting, now we're looking for the largest multiple of 15 that doesn't exceed 80, and that's 75. 75 is 15 times 5. That means we put a 5 to the right of the decimal point. And now when we subtract what is it? Yeah, 55 from when we subtract 75 from 80, we're left with 5. We already did that. 50. Now we look for the smallest multiple of 15. That doesn't exceed 50, and that's 45. 3 times 15, which means we have to put a 3 next to the 5. But then if we do that, if we subtract 45 from 50, we're left with 5 again. So this is exactly what we had last step. That means everything's gonna repeat like it did last time. We're gonna get a repeating 3. This is a period of 1. So we get 0.53 repeating. So it didn't start repeating right away. Notice, unlike the example for 1/13, that one started repeating right away after the decimal point. This one starts repeating, after 2 steps, but the period is 1. So we have what's called a pre-period of 1 and then a period of 1. And in general, that's what's going to happen. You're either going to get something that terminates or something that repeats. It might start repeating right away, or it might start repeating after a while. But eventually, it'll start repeating. Anyway, that's how all decimal expansions look for rational numbers. And that's just 3 examples, and I think that kind of covers everything that can happen. So you can try your own examples if you want. Anyway, now you know how to do it. So that completes my video on how to convert from fractions to decimals. Thank you for watching. Long live math, and I'll see you guys next time. Bye.